Hi there, I'm Trace, and we're finally here. Final analysis for my current design, and yeah, it's been a long journey. And long story short, it's not going to work. At least this current design. And so let's go over it. The reasons why this design's not going to work. The let's jump into it. Let's go over some of this. Let's take a look at this combination here. The this combination with the 8 magnets on the stator and 5 magnets on the rotor. All right. So let's move the rotor around a little bit. Give me a moment. All right, let's take a look at the model here, or the design. And if we were to rotate this, and we're looking at this one magnet up here, right? It's gonna have a lot of resistance right here, just for that one magnet, right? And it'll reach a point, like right in this area here, where it sort of zeroes out. It sort of balances, but it's an unstable position. It's gonna want to go one way or the other. But the thing is that this resistance here, get to a point where you get it zeroes out, and then it wants to push, right? Well, that resistance right here equals the same amount of force pushing it. So it just sort of balances out. So there's no way to counter that. You actually need a little bit more. You need more push than you have resistance. Like right in this area here, needs more. And when we're looking at the math model here, like here's that sine wave for that one area there. And if we're to look at that, it's not necessarily a sine wave. It's just a function, but it's definitely a wave. Let's take if we were to do an integral with the area, we're looking at, you know, a negative here, negative area. But you know, like we talked about before, it's 0, right? So the negative portion, which is this area plus this area, that will equal, like if we're looking right here, that's going to equal this right in here, right? That resistance. And then you have your positive, which is your push. If we're looking right here, you got the resistance, and then you got the push, right? Well, those two areas, the bottom and the top, equal out. So it's just the sum of it is 0, right? So, and if you look at the other magnets here, they have their interactions too, but in one full revolution with all those interactions, the total sum is 0, right? And I thought that we could overcome that by a different design on the magnets, how they interact, like how they cross. You know, can they cross differently to manipulate the sine wave right here, or this wave, in such a way that you get a more area on top than the bottom, or vice versa. It doesn't really matter. Let me demonstrate a particular line here. So we got a area for this integral at 0.0004, well, negative 0.0042, right? And if we were to look at a modified version of this right there, right? Function 25. You see, I clipped the bottom of this area here. So it's, let me delete this, hide this. So I clipped the bottom of that function. So the total area on the bottom of this function is, it's going to be out of balance. So let's do an integral of this one. So now take a look at that. Now we got a positive 0.4901, which is dramatically more, it's like out of balance. So you definitely have more area on the top than the bottom. And now we could plug that into our total math, excuse me, our total math model, right? And so let's take a look at that. Let's zoom out a bit. Well, actually, let me hide this. Delete. Delete. Hide these points. All right. So let's zoom out a bit. Let's rescale the window. No, I don't like that. Yeah, that's better. All right, let's do an integral of, let me hide this function here. Delete or hide. All right, let's do a integral of this. So that will be, remember when we did it before, we have, let's look at this right here. Like if you're looking at this interaction on the rotor, so the ones in the blue are the magnets on the rotor, the ones that are darkened are the magnets on the stator, right? So if you look at this one full revolution, we're going to have 8 interactions, right? So that one magnet's going to have interactions with 8 magnets on the stator, right? So all the way around. So that would be represented by this function right here. So that one magnet, one full revolution, we're going to have a, let's get an integral of this. Give it a moment. Computer's bogging down a little bit, asking a lot of it. All right. So yeah, look at this. We got some, we're getting some area here. Now that would be just one magnet on the rotor rotating 360 degrees, right? But we actually have 5 magnets on the stator. Excuse me, 5 magnets on the rotor and 8 magnets on the stator. So we would have to take this one right here, this number, control copy, and multiply that by times 5, right? So yeah, we have a dramatic difference. So, you know, that's just demonstrating what we're looking at. That's sort of what we need is sort of a wave that has different areas for either the top versus the bottom. But how do you do that? I know that there's some people try to create shielding or of some sort of mechanical mechanism to try to change that wave, but that just takes energy, and that's just not feasible. That's just not something that's going to work here. Let's move on to. And so I have a quick little video of the data acquisition system. Take a look at this. So here we go. So take a look at this here. My initial thoughts were that we could move these magnets back and forth in such a way that how they cross each other, the profile would change, right? And I could definitely get that, you know, like this here. Could rotate this around. Let me lock this down. So when it crosses over, right, the profile is different. So I'm able to change the profile of the sine wave. Definitely the shape of it changes. But what I thought I was going to be able to do was change the areas of the positive versus the negative. I mean, in such a way that one would have greater area than the other. So, and I wasn't able to do it, no matter what angle I rotated this, you know, back and forth. I tried quite a few different combinations, but the result was the same. The area underneath the x-axis on the function, the final function, would always equal the area above the x-axis on the final function. So it's just a no-go. So another thought that crossed my mind is if I was to add up these, like if we take a look at this function here, let's take a look at this one here. So let me turn this one off. Hide. So again, if we are to take another look at this function here and do an integral, right? You know, we got a negative 0.00041, and you know, like we discussed before, it should be 0, but nonetheless, that's close enough. Now, I thought that possibly changing up the combinations in such a way that maybe when you add up the how the interactions, sort of like the combinations of the magnets, right? Maybe that would change the total area. So let me go over some of my thought processes there. So let me delete this or hide that. Delete. So that was negative 0.0004, right? Delete. So we got that function, but now I'm adding up two functions here. So we got this function 21, which is this guy right here, and it's phase shifted over a little bit, just so it's the beginning of this function is at the very beginning. And then, so that's function 21, and then we take function 21 and we add it to itself, but when we add it to itself, the second portion is just phase shifted just slightly here. So now, if you recall, our total area of this was, for the first little bit here, is, I don't know if you could quite see it here, it's negative 0.00004. But now if we continue on, we got negative 0.0008, right? So take note of that. Let me undo this. So let's take this function, and I was thinking that if we just shift it over, right? So they interact in such a way that possibly we could get a change the area that way. So let's phase shift this over just a little bit. Let's go 20. Let's go a little bit further. Let's go 30. All right, so you could see how it sort of shifted. I'm thinking possibly that way we could get a different area here and manipulate the waves that way. But then if you take an integral of this, it's essentially the same thing, right? And that's our initial error times 2. So we have two waves with the same error, the same amount of error on it. So, but let's say we wanted to keep on trying to see if we could come up with a different combination here, and just phase shift it a little bit, even just a little bit more. Let's go a little bit further than that. Let's go 60. All right. I mean, now it's really changing here, and you get an integral of this base, and still we're coming up with essentially the same number. So what I found was, no matter what combination, no matter how much you shifted it, the outcome is the same. So let's go 100. I mean, look at this. I mean, it's really, you're getting some awkward shapes here. Let's go analysis. So it's not quite, I mean, again, not perfect, but it's getting it's coming up with essentially the same thing, and it's 0, right? We went over it quite a bit. So I was thinking you could come up with a unique wave where you could actually have some either a significant change of area either on the bottom portion of the function or the positive portion, where you have a difference, right? Where you could get the motor to drive, but that's just not the case. So I tried that with the data acquisition system by manipulating the magnets back and forth and trying to come up, manipulate the, well, that was my first initial try, was that. And then my second try was with the different combinations. And I mean, look at this. Here's an example of some of the different combinations I came up with. I mean, we went over, what, 3 or 4 different combinations, but there's many more that I came up with. For instance, take a look at this. This is a combination of with 23 magnets on the stator and 23 magnets on the rotor, right? So we could go, oh, you can't quite see all that. Let me shift this down. So took this function and phase shifted it over a little bit until I was able to get a total area. And you can take a look at this. This is a combination of 23 magnets on the rotor, 23 magnets on the stator. Okay, added up all that. So this would be the final function. If I was to take an integral of this, it'd be 0. But fine, take a look at this. I came up with another one, right? This is 22 magnets on the rotor, 23 magnets on the stator. And look at this, you can see how it just sort of just cancels out. So let's zoom up on this. Escape. Yeah, just totally hide. Yeah, you can see that combination just completely just cancels out. And here's another. You know, this is 21 magnets on the rotor, 23 on the stator, right? And I meant that essentially flatlines to almost 0. Here's 20 on the rotor, 23 on the stator. Yeah, look at this. Let me zoom up a little bit closer. Yeah, so I have many more combinations here. Yeah, it's starting to come through here. So, I mean, I went from, so this would be 1 magnet on the rotor, 23 on the stator. So all these combinations that I have on this one page here have 23 magnets on the stator. The only difference is the amount of magnets on the rotor. But no matter what combinations I come up with, it's the outcome's all the same. And I have many more functions, like this one, for instance, is combinations with 22 magnets on the stator. So all these combinations that I'm coming up with right here are 22 magnets on the stator, and then different magnets on the different quantity magnets on the rotor. And like this one is 21 magnets on the stator. This one's 20. And so I just have so many different combinations, and the outcome is all the same, every one. So it's the trying to come up with a scenario where you could come up with a combination to change this sine wave or this wave here in such a way that you get different areas from the top and bottom. It just, with this design, it's just not possible. So that's where we're at. This particular design is just not going to work. But stay tuned. I think I got something else for you. I have a new design that I'd like to share with you. I'll cover that in the next video. The difference on that one, we'll cover the differences on the next video. But until then, guys, yeah, fortunately, this design is not going to work, which is, it's okay. We'll move on, and we just have to sort of expand our vision, if you will. And we'll see about coming up with different strategies on how to get this thing done. All right. Until then, guys, peace.